Welcome to the second talk of this session. The speaker is Professor Yitwah Cheung from Yale Mathematical Science Center. He's an expert in dynamic systems ergodic theory, and he's going to talk on Perez Marco for simultaneous approximation. Let's welcome Professor Yitwah.
Thank you. I appreciate the opportunity to tell you about a very interesting result. I hope I do it justice. This is work in Yumin Wei's PhD thesis. And I will mainly, my goal is maybe to motivate the results which involve both ergodic theory and Diophantine approximation. And there's a lot of motivation. So I'll start with the ergodic theory. And I'll start with a dynamical system that is very easy and a high school student will understand. You start with a polygon. So this polygon, think of it as in the complex plane. And in the polygon, you can play billiards. So the trajectory of a billiard travels angle of incidence equals angle of reflection. And I want to assume this is a rational polygon. So these angles, interior angles, are rational multiples of t. Okay. Then so this is the ergodic theory of rational billiards. So I'll begin by explaining one story which goes from about 30 years or 25 years. So it starts with a result of Kirchhoff, Maser, and Smiley. And the statement is that for all rational polygons, P, the set of directions, so Lebesgue measure in the unit circle of the non-uniquely ergodic directions is equal to 0. So here I'm just going to say really briefly what I mean by NUE. So UE is my shorthand for uniquely ergodic. And N just stands for non-uniquely ergodic. Okay. So what we're saying here is that if you have a direction, if it's uniquely ergodic, what it really means that there's a dynamical system that is determined by your kind of initial direction that you shoot the billiard ball. Okay, and this dynamical system, as you might guess, for almost every direction, the orbits will be uniformly distributed, and this is the equivalent to being uniquely ergodic. So I'm being a little vague here. Everything can be made precise, but what it means is that every orbit starting in the theta direction is uniformly distributed. So the amount of time you spend in an open set is proportional to the area of the open set. So this can be made, so to give a slightly more, you might ask questions like, what happens when the billiard hits the corner? And you can answer those questions. You can continue, but you should continue in a certain way. These ideas are made precise. To each direction, there is a dynamical system, a flow, or more precisely, a measured foliation in the sense of Thurston, which is on some high genus surface. And the reason you need the angles to be rational multiple of pi is so that when you try to understand the dynamics, you kind of unfold the table and you close Riemann surface out of it. Okay, so underlying here, I'm going to suppress a little bit the complex analysis that shows up behind, but there is this closed Riemann that you build out from this table, obtained by unfolding. And there's also this holomorphic one form, which records the geometry, the Euclidean geometry that is intuitively obvious to us. The holomorphic one form is induced by BZ. So I'll just tell you a little bit about, like, I won't tell you everything. I'll tell you just the exciting results during this period in this direction. And so there are many polygons you can study that have satisfied this property. And the basic example is if you take a rectangle and you play inside a rectangle, and you kind of easily can figure out what happens there. As a result of Veitch, which is very interesting. So SL of X omega is the affine symmetry group. You can look at the set of affine diffeomorphisms of this closed Riemann surface to itself. And if this is a lattice, so it naturally embeds into SL2R. Then this implies that the dynamical system is very similar to the case of a rectangle. So here, every direction is either uniquely ergodic or a union of these completely, so it's a completely periodic, meaning that the orbit in every direction closes up. You get the surface decomposes into a union of cylinders, okay? So this is a disjoint union because either all the orbits are equidistributed inside the table, or they all close up. So the two extremes of possibilities. So that's a beautiful result. And I mentioned this in particular. It follows that the set of non-uniquely ergodic directions is countable. It's not entirely obvious, but it's a consequence. Okay, so if you think of a square, then you either have irrational or rational, and the set of rational directions is countable. Now I need to mention a result of Mazur. And here is, so we're interested in the dynamical systems in the table, but there's also another object, which is the closed Riemann surface. And this closed Riemann surface, you can deform it by what's called the Teichmuller flow. So this defines, this is like, this is sitting inside the moduli space of Riemann surfaces. So I'm not going to write too much here. But the statement is that, this information here is determined by, so we have a X, we have a closed Riemann surface, we have this direction. And the statement is that in this kind of setting, I'm going to be very terse here. If we have, I'm missing something here. So when I don't say what theta here, I think of it as being the vertical direction. So this is the vertical. And so if the vertical foliation is non-uniquely ergodic, then you get this trajectory sitting inside the moduli space. I usually draw a little picture like this. This is the moduli space, and we have a deformation of the Riemann surface, and it will kind of like leave every compact set. So that's what div means here. It's divergent. So the second result that I want to mention here is that the Hausdorff dimension of so it's the next question you would ask after you know that almost every direction is Lebesgue measure zero is how big is this exceptional set of measure zero? Can it have any Hausdorff dimension between 0 and 1? And what Mazur's result says is that sorry, this is a little cluttered, but the answer is that the Hausdorff dimension is at most 1/2. So these non-uniquely ordered directions are always going to determine a divergent trajectory in the moduli space. And the Hausdorff dimension of those trajectories in this, as you rotate the surface, cannot exceed 1/2. Okay. All right. So maybe I should say that this object or the function, the Hausdorff dimension of the set of non-ergodic or non-uniquely ergodic directions, this is an invariant for some SL2R action on some moduli space. And so this is an interesting object, and people ask questions about it. And their results, Mason and Smiley, I guess I've mentioned them before, that Hausdorff dimension 0 is rare. I'll just say it that way. Okay. So for every Riemann surface with this holomorphic one form, you can look at this set of directions, and we know it's a set of measure 0. We know the Hausdorff dimension is at most 1/2, but and it can be 0 sometimes because you have these beautiful lattice surfaces, we call these, and they're a countable set. A countable set has Hausdorff dimension 0. And but Hausdorff dimension 0 is rare. Rational numbers are rare. But can we give some explicit examples? And the first explicit examples will come. So I'll mention, so if we consider this is a 2x1 rectangle, and we put a barrier, say, of length lambda. Lambda is a real number between 0 and 1. Then in this case, it was shown by Bushnishyn and Cheung that that the Hausdorff dimension of this table. So you play the billiards in this 2x1 rectangle, but you have a little barrier, and this is equal to 1/2 if lambda is Diophantine, which Kanin just explained to us what it means. So if you satisfy if this real number satisfies a Diophantine condition, then you will actually achieve the largest possible Hausdorff dimension. And but it was known, in fact, it was known to Bushnishyn that there exists a residual set, in particular an uncountable set of lambda, such that the Hausdorff dimension is equal to 0. Okay, so this was maybe 20 years ago, and well, I think it's a nice result, but you can ask what is the condition that you need, what about other values of lambda? Can you produce other examples? And let me say, this one problem that we have no way of tracking is that we do not know of any example where the Hausdorff dimension is strictly between 0 or 1/2. So the only known example either 0 or 1/2. And it turns out that I should say that at this point you turn to other problems and you say, well, it's a nice answer, and you think about other problems, but you come back to it, and later I came back to this problem, and we were able to. I'm gonna get to 2011. We managed to actually compute this and show that dichotomy holds. So the Hausdorff dimension is either 0 or 1/2 for all values of lambda, and the condition for which it holds depends on the continued fraction of lambda. So here, let me put lambda, you can write as a continued fraction, as a simple continued fraction, like uniquely. And if you truncate the continued fraction, you get this sequence of rationals called the convergence, as Tanin was saying. These are, especially the denominators, are very important. And I really like that remark. It's also very, very important in my talk, this sequence of denominators. And here, Perez Marco means that if you take the series log qk plus 1 over qk, this thing is summable. So in other words, if the length of your barrier, you take a continued fraction, satisfies this, you get 1/2 as the dimension. Otherwise, you get 0. Okay, so that's one thread of the story. This answer is complete within this one real parameter family. Okay, but it's somehow not satisfying. For this, there's dichotomy for all real lambda between 0 and 1, either 1/2 or 0 for the dimension. Yeah, so you get 1/2 for this. Sorry, I should say this implies Hausdorff dimension 1/2, and if you have equal infinity or rational, then Hausdorff dimension is 0. That's the statement. So it's really mysterious, this condition, the Perez Marco. This condition shows up in holomorphic dynamics in the linearization problem. Yes? In the middle. Yes, this is right in the middle. I don't think so, but that hasn't been studied. I mean, I don't think it's essential. I think if it's yeah, I won't make any guess. But okay. So now this problem is mysterious. We don't know how to find any examples of this, so we're not going to touch that question. This condition is very mysterious. It shows up after lots of consideration, which I cannot explain to you, but it shows up. It's the answer, right? The answer shows up to this ergodic theory problem, this number theory answer. And I want to, and it involves the continued fraction. So the continued fraction is dragged into this ergodic theory problem. Okay, but I want to say that this answer is unsatisfactory. It's unsatisfactory because when we unfold this, okay, I'll tell you later why it's unsatisfactory. Okay, why is it unsatisfactory? So because the surface that you get when you unfold it, so I call this x lambda, okay, it's two tori glued together along a slit of length lambda, okay? So there's something called a slit construction. You cut open along this horizontal slit, and then the trajectories kind of enter here and go out there, and if you come in here, you go out there. And this forms a genus 2 surface with two simple zeros. And the theorem here is really a theorem about this surface. okay? And it's unsatisfactory because you might say, well, why don't I take a slit which is not necessarily horizontal, okay? Then it's more complicated because it would involve this pair of real numbers. And you would naturally guess that you still get dichotomy, okay? But what would be the condition for formulating, like, what's the generalization of Perez Marco? Because we know in higher dimensions, we do not have continued fraction theory. So I'm going to give you a definition. So I'm going to work in general. So I fix a norm in Euclidean space of d dimensions. It doesn't have to be Euclidean norm. I choose other norm. Given any point in d dimensions and a rational. So here, when we write rationals, we always write them in lowest terms. So GCD of PQ is 1. This is an integer vector in d plus 1 dimension. Lowest term should be, the denominator should be positive. Then we say this rational is a best approximate to theta with respect to this norm if you write something like q theta minus t, take the norm of that, and that achieves the smallest possible value of, say, n theta minus n among rationals with denominator less than q, less than or equal to q. There are so many norms, you're absolutely right. And so one thing that should make you hesitate, you might say, oh, yes, I can take this notion. In fact, that's what we're going to do, okay? And you pick, say you fix some norm, you define this notion of best approximate because we know by the theorem of Lagrange, in one dimension, you are a convergent of the continued fraction if and only if you're best approximate of this type. And but here, in higher dimensions, it depends on the choice of norm. And so you would have to ask the question, if I try to generalize this to this vector situation, what would happen, which norm should I pick for this to be true? Okay, so it turns out it doesn't depend on the choice of norm, but it's a corollary of our result. So let me, okay. I think I have to mention that, so I've mentioned Lagrange already. And the theory of best approximation isn't, I don't think it's heavily studied, okay? But Lagarius, oh, I should say there's Castles. People certainly have looked at this notion. Lagarius started to systematically investigate it in the 80s. And Chevalier has some work on it, and there's certainly many others. And I got involved somehow. I needed it for something. And I want to mention some results. So if you define it this way, choose your favorite norm, okay? Then you can get some estimates like this. So there's some factor of 2, but upper and lower bounds, the norm of some integer vector. So if you're familiar with continued fraction, this will be familiar. So MK is like, it's an integer vector which is kind of formed by kind of cross products of the dk and dk plus 1 and the qk and qk plus 1. So it's kind of like a cross product. There's also another version of this there's a set you can define. I call it the domain of approximation. The domain of approximation of a rational. So you take all the theta which satisfy this condition for a given P over Q. And this essentially is a ball about centered around P over Q with some radius which is like Q to the 1 plus 1 over D, but weighted by some lambda 1 hat. And lambda 1 hat, this is the normalized minimum, first minimum or systole, many different names, of the lattice like that. So you mean here, this means upper and lower bound with a factor of 2. So yes, oh, sorry. This means you have B something radius over 2 contained in delta contained in B 2R. That's what it means. Okay. I should maybe have typed everything in using these tricks. Okay. Sorry, what's the question? MK? MK is, okay, all right. Okay, these are integer vectors. The B here is kind of like a PQ. It's an integer vector. You do a cross product. It's a second exterior power. I don't want to get into it because it's, but that's what it is. Okay, so Yumin's thesis says, oh, I've already told you what it says. If, no, I haven't, but well, something like that. If lambda mu satisfies Perez Marco condition and 0 otherwise, and the corollary is that for dimension 2, the Perez Marco condition is independent of the choice of norm. So this is an application to number theory. You see, Perez Marco condition is something you can define just because you're doing number theory. And but it seems from the definition that it might depend on the choice of norm because the sequence of best approximate certainly depends on the choice of norm. Huh? Log. Yes, log. One log would be Bruno. Okay. So we get as a corollary that is independent choice of norm. We do not know if the Perez Marco condition in dimensions 3 or higher is independent of the choice of norm. We really need ergodic theory to get this corollary. Okay. We don't know. In fact, even in one dimension, it is independent choice of norm, of course. Okay. All right. So that's the main result. So I want to now kind of explain the broader context. Oh, yes. Mu is the y coordinate, y component of the vector. So this was the real case. So the special case before was when mu is 0. Okay, so right now we're taking a vector like this, lambda mu. Yeah, and we still, yeah. And for that surface, we can consider the set of non-ergodic directions, and you get this result. We've gone down the rabbit hole. It's just curiosity. We want to know. We can get an answer, and But it took a while to really find this. And so now I want to kind of recall, so that maybe a subtitle of this talk is a class of generalizations of continued fractions. And there is, as I mentioned, there's a nice class of generalizations to higher dimensions, but generalizations don't have to go to higher dimensions. And the one we need to use here, apart from formulating this where we go to dimension 2, we have a different generalization. I call it the higher genus generalization. And for lack of a better name, they're called Z expansions. So Z here is a subset of R to the D plus 1. D will be 1 in our applications. So actually these generalizations it's appearing in higher dimensions here, but it's appearing in one dimension here. Okay, so I need to recall. So here I'm only going to be sketching kind of the ideas. So we have these, I'm back to kind of like translation surface or these billiards. I have these non-uniquely ergodic directions. And there's this result of Maser, which tells you that every non-uniquely ergodic direction, the corresponding dynamical orbit in the moduli space leaves every compact set. And this containment was Maser. And so let me say that there's an analog of Mahler's criterion. If you've never heard of this, I'll just say what it is really quickly. So our moduli space, think of as some finite volume non-compact space. The baby model for this is if you take SLNR mod SLNZ. So this is an example of that. And there's a lot of dynamical systems, homogeneous dynamics on this space. And here, if you tend to infinity, if you leave every compact set, so this could be the space of lattices, going to infinity, what Mahler's criterion tells you is equivalent to saying that the length of the shortest non-zero vector, which we'll call systole here, this goes to 0. Okay, as t goes to infinity. So that's what it means to go to infinity, and there are similar versions of Mahler's criterion in the moduli space of Riemann surfaces. I will just mention the concepts. So the L1 here is a different concept of measuring the shortest vector. L1 here is the shortest saddle connection. So on these surfaces that we get, these are called translation surface or holomorphic quadratic differentials. They have singularities, and if you measure the length of the shortest distance between two singularities, that's the length of the shortest saddle connection. But you can consider more interesting objects. You could require, so a saddle connection could be an embedded segment, and you could measure something like the shortest essential simple closed curve. And then you could even measure the shortest, what's called separating system. So on a high genus surface, a simple closed curve may not separate the surface. So you can require that you have the complement has to be has more than one component that is a separating system. I'm not going to give precise definitions, but you might guess the relationship between these different ways of measuring length is that the shortest separating system is longer than the shortest simple closed curve, is longer than the shortest saddle connection. And the reason I'm mentioning this is, so from these inclusions, this would be divergence 1, divergence 2, and divergence 3. And there's a result here with that Alexeskin where, again, if the foliation is non-uniquely ergodic, then the trajectory determines it actually leaves every compact set in this, what might be called a partial compactification of moduli space. So there's a stronger notion where the length of the shortest separating system is going to 0. All right, so maybe I will. So now back to our situation. Our situation, we have a surface, we have the slit. We call this a holonomy vector. Holonomy vector is a pair of real numbers lambda comma mu. And we can form the set Z is a set of pairs lambda plus 2n mu plus 2n. So it's m and n are integers. Union set of primitive pairs. So these are examples of what are called separating slits. So they correspond to, you might have on this surface here, you might figure going around some other direction here. Something like this. And that turns out to be another, an element in here, which it separates the surface in the sense that if you think about the construction of the branch double cover of the torus, the white slit and the yellow slit gives you biholomorphically equivalent branch covers. Okay, so using this result with Alexeskin, we can show that, so we can define, so whenever you have a subset, a discrete subset of R to the D, then you can define this generalization of continued fractions theory using this idea of best approximates. And using this particular Z, we can show that there's a symbolic characterization of what it means to be non-uniquely ergodic. And it means that the Z expansion, so previously continued fraction expansion was a sequence of rational. The Z expansion will be a sequence of slits or loops. These guys are called loops. They correspond to cylinders. So we have the Z expansion. It will actually eventually alternate between separating slits and loops. Well, let's write this way. And moreover, if you write down this cross product, this is just the area of the parallelogram they span. You write down this series, this is a summable series. It's not hard to explain this, but I need to talk about the surface and just leave it. But this is summable cross products condition. This is it's needed. So now I can sketch kind of like the proof of this result. Perez Marco was not show up here at all. Okay, here I was just introducing the concept of Z expansion, and I was explaining using Cheung-Eskin here, one can characterize what failing to be ergodic means. And there's a symbolic characterization purely in terms of the Z expansion of that direction. Okay, and now we want Perez Marco to come in. I'll tell you right away. Okay, so it comes in when we do the upper bound. So first thing, to prove this, we already know there's a general upper bound of 1/2. So there's just two things to do. Prove Hausdorff dimension 0, that's the upper bound. Okay, so upper bound means if you don't satisfy Perez Marco, if lambda comma mu doesn't satisfy Perez Marco, then you get Hausdorff dimension 0. Okay, how does that work? Well, actually, this was maybe already observed by Yang Huang. And well, okay, that's enough. So if you are non-uniquely ergodic, or not going to really distinguish here, then the key lemma is that if the direction is not uniquely ergodic, then theta is z Liouville. Okay, so the notion of a Liouville number can be understood in terms of this z expansion. Okay, and Liouville numbers are well known to have Hausdorff dimension 0, and that's true for the z version as well. And so you need to prove this connection here, and the idea of this argument is that if you're not Liouville, if you're not z Liouville, well, then that tells you that in your kind of z expansion, these vectors kind of don't grow too fast. There's some upper bound on how fast the lengths of these vectors grow. And this leads to a contradiction. Basically, this condition contradicts the divergence of the Perez Marco condition. And I'm not showing you, this is just a sketch, but how it works. So it's really sweet. In fact, the lower bound argument is way more intricate, but in a sense, the key important idea is kind of recognizing this concept of z Liouville helps you to prove dimension 0. So for the lower bound, here you have to do a construction. So you're looking for sequences. So you're building because this is an if and only if. So you're building sequences that satisfy this condition to build non-ergodic directions, and you're going to build a counter set of different directions, and you have to solve this counting problem. So let's say you've built the J slit. Then you look for integer vectors which satisfy these inequalities. So you want to control the length. You build a nice set where the growth rate of the lengths are reasonably controlled, and you control the cross products. Of course, you want to find a sequence where the delta j's are summable, and so that's the counting problem. It depends on the choice of a sequence of the delta j's. And the point is, given the Perez Marco condition, we're in this log qk plus 1 over qk full pair lambda mu. This suggests how to pick the delta j. I can't explain exactly how, but you have to choose the sequence according to how this thing is according to this condition. Okay, how much time do I have left? 15 minutes. Okay, good. So I won't tell you exactly how we choose this, but I will say that the problem here, we have a slit wj in the plane, and we're looking in a region, and these vectors v are primitive vectors. So the problem is to count primitive vectors in some region which looks like a rectangle, and this rectangle has very large area. So you expect the area, a constant times the area in there, but when you actually have to do it, and you have to be able to do it forever, in this recursive procedure, that's where it gets challenging, subtle. So we have this, I'll just say, recursive procedure. for building these sequences. And then the challenge is to always have enough children at each stage. And enough children means at least a constant times the area of this region that I've indicated. And in order to guarantee this, in order to guarantee that you get enough children, that's actually very, very tricky. And this depends on kind of like the Diophantine properties of alpha j will be the slope of wj as a vector. And if you take the sequence of denominators of alpha j, this has to have some kind of there's a denominator in some interval for some t. Okay, and then that's the nature. It's very complicated, but there's some condition like that, number theory condition, which you need to satisfy. And so the new element, which Wei uses very well, but I can't explain, and it's not my goal to explain it either. But she uses this notion of nearest linear form, which is a notion to being a best approximate. So best approximate is approximation by the lowest dimensional, zero-dimensional subspaces. And linear forms is approximation. You can think of it as approximation by codimension 1 subspaces. And the nearest rational linear form, she uses that to construct best approximation denominators. So some very smart combination. You have the nearest form. You see what you need to get, and 1 is not enough, and she takes 2. And the other one also not enough. And in the worst case scenario, when neither of these works, there is some intersection which she can guarantee is kind of like a best approximate to standard mu. So I'm just giving a flavor of the new ingredient that is needed to make this work, and it's fascinating. But okay, so I'll have some final remarks. Why is this interesting? And not just the curiosity. Okay, it's certainly the ergodic theory, I think, well, it's really turned into number theory, it's not ergodic theory. And I think of the Z expansions as a general framework for getting finer Dani correspondence. And let me just say briefly what brief remarks. So there's this general correspondence between number theory and dynamics. On the number theory side, you could have vectors or linear forms which are badly approximable. And they translate into orbits of homogeneous systems. And you get these like bounded trajectories inside a homogeneous space. And this correspondence generalizes very well to other settings. There are also this concept of singular vectors. And here they correspond to divergent trajectories that leave every compact set. And in some sense, what happened in the context of the Teichmüller flow, it was discovered these non-ergodic directions, which are special divergent trajectories. I should say that the theorem that we can ask the same question for divergent trajectories, and the Perez Marco condition does not. You do get dichotomy, but it's only if it's irrational. It's not. The Perez Marco condition doesn't show up. These kinds of correspondences kind of has a long history, and there's another type. There's Khinchin's theorem, and Khinchin's theorem corresponds to the Sullivan's log law. Sullivan wrote an influential paper in the 80s, and you can measure kind of like the limb soup of the distance at time t. So we say your initial point divided by log t as t goes to infinity, and this is equal to some constant which we can compute in many different settings, and this is equivalent, or it's a dynamical interpretation of Khinchin's theorem, which is still people are proving theorems about this, and I'd like to mention this Levy's constant, which is the growth rate of the approximation denominators. So it's something like pi squared over 12 log 2. This is generic growth rate. So this is almost every real number. And with Chevalier, we can generalize this to higher dimensions. So this is, well, let's say d greater than or equal to 2. We can't quite compute it, but we can prove existence. And this is the nice thing about this and this, you need to use a little bit of ergodic theory. Okay, whereas these are almost like tautologies. And the spirit is that these correspondences are very soft. These correspondences, like here in I again use I choose a norm, and I do best approximation with respect to that norm. I order them, and this makes sense. And it will depend on the norm. We don't know if it depends on the norm, but presumably it does. Okay, and but I want to say that what I want to say last is what are the things that we still can't do. So we have generalizations of continued fraction theory, and it allows you to do some things like Khinchin-Levy theorem. It can do that. It can do all these things. Khinchin's theorem, Sullivan log law. That's already been done. But what are the things that it still can't do? Okay, and what I want to say is that the point here, the continued fraction, if you have your, let's say, alpha, before I call it lambda, but if it's the set notation, if this is your continued fraction, the relationship between the terms of the continued fraction, the partial quotient, and the sequence of denominators, well, you can easily deduce this. If Q0 is 1, Q minus 1 is 0. And thank you. So we're building the theory on this sequence instead of the sequence of partial quotients. And I'll be very, very short here. So you have a function. We know this function is almost everywhere equal to this number. It is expected, it is maybe known, that if you compute, this is the Hausdorff dimension of L inverse of a number, it looks something like this. So the almost everywhere constant is where the Hausdorff dimension is equal to 1. This is pi squared over log 2. I guess this would be the log of the golden ratio. And this is 1.5. And it's a result of Fan Liao Wang Du. I think in 2009, using thermodynamics. This is real analytic. So in particular, when you know it's real analytic, then the maximum is uniquely achieved, and that gives you non-trivial Hausdorff dimension inequalities. This is a result that uses the thermodynamic formalism. Thermodynamic formalism we don't know how to do it yet because we don't have the generalization of the symbolic dynamics. We have this kind of generalization, which you can, depending on what you mean by symbolic dynamics, I mean, we can achieve a lot of things, but we cannot achieve kind of this kind of result. There's some other kinds of results, like the results of Gugu-Moreira on the Lagrange spectrum, which I don't think I should bother you with. But again, there are some very, very fine results that depend on stronger properties of the symbolic dynamics that we currently don't have. And so this problem is open, proving that the Levy constant, does it have a real analytic Hausdorff spectrum? That's I think, most pressing open problem that I want people to address. Another one, if you know what is Hall's ray, the existence of Hall's ray is also open in higher dimensions. Hall's ray in Lagrange spectrum. These are things that you would think the symbolic dynamics would be fine to solve. And so this is the measure of how good your symbolic dynamics is. So these are two open problems that I recommend for other people. Thank you for your attention.
Okay, thanks for the nice talk. Any questions?
One surprising thing you said, you expect that the Levy's constant analog will depend on the norm here in the high.
We cannot.
You cannot rule it out.
I cannot rule it out. So the space of norm is infinite dimensional, and the Levy constant would define a codimension one subspace of this infinite dimensional thing. And how do you detect whether you're moving off of?
But just if you take two norms, so you expect that the log is very contracting function. So you expect that in one norm you'll have a lot more best approximations than in another norm. This is
I'm sorry.
I would guess the opposite. But do you have any evidence? I mean, why do you think? I understand you cannot prove it now, but what you conjecture? You conjecture that it will depend on the norm.
No, I don't. I once conjectured it doesn't depend on the norm, but then I realized I have no way of proving it. So I really don't know. I really don't know. It would be also, it would be surprising if it doesn't depend on the norm. Not for you. Okay. At some stage, I was.
Could you have like both of these could be like, could they be 2 to the k in one norm and 3 to the k in another norm? And it's skews. I mean.
Yes, that seems unlikely.
But proving is hard. Yeah. But
there's no algorithm for calculating.
What? Absolutely. There's no efficient way. I mean, you can't determine them in principle.
No, you can define them, but there's no algorithm.
Yes.
Good luck.
So I mentioned the domains of approximation. They're actually very delicate objects, and like studying these things are kind of like the algorithm.
Let me make a remark. The theory of multidimensional continuous friction is very old.
Yes.
And you did mention what is called Jacobi-Perron algorithm. Jacobi wrote certain algorithm. He was not satisfied with it, and he didn't publish it. It was published after his death. So he was not maybe And Perron actually developed the theory of Perron theory.
Yes.
Was studying this algorithm.
Yes.
Correspond to multiplication of
Yes.
matrices. Then there are many properties similar to continuous fractions, but and then you can say it's the best, but in a very restricted domain. So domain where this is the best is kind of degenerate. So it's best here, but maybe outside it's
Yes.
not the best.
But there are like some
So
papers
that's a
of
multiplication.
Lagarius in the 90s.
Lagarius in 90s was using another way. This was
Correct.
homogeneous.
Well, he had two papers in the 90s at least.
Yeah, so
And one was, I think, was basically saying these Jacobi Perron, Selmer,
was
these,
not good.
they're not good.
They're not good. And
They
they
don't
are
give
not
you best approximation. The exponents are actually not sharp, even the exponents.
good. You get numbers, you get universal numbers, but they are not best approximation for other norms. So it's,
Yes. Yes. Yeah. So we give up on the algorithm. Oh, are we? Exactly. That's correct. 8K does not make sense. So you're saying that's only in dimension one. Oh, you can define. Yeah, you can. I mean, okay. So I'll give you an example of a problem which so um, so it's more subtle that that there's a this is not the interesting invariant. No, it is interesting, but the sequence of best approximates is maybe not the right sequence. That you maybe need to go to a subsequence that is more efficient. In the case of the best approximates, in some of my work, what happens is that there's a natural subsequence, not easy to define, but there's a natural subsequence in dimension two. There's a natural subsequence. In higher dimensions, it's not clear what's the canonical kind of. It's not very canonical, but there's you need to the symbolic. There's more to uncover. And there are many quantities you can define, and it's like which one is the most interesting. This is interesting, but you may need to pass to. You still have to define the interesting subsequence for which this is interesting. This is related to the depth, and exactly how it's related, we have detailed information. Yeah. So in higher dimensions, what's going on is that it's not just the systole, the first minimum that matters. You have second minimum and third minimum, and so you need to keep track of the entire profile of all the minima. And we understand how these behave, and we also have a model for the combinatorics and how they change from one setting to another. But this is still being in development, I would say, and we don't have a simple, nice answer. We can construct interesting examples and disprove conjectures or whatever, but yeah.